So, without any further ado, we want to welcome Professor of Psychology and Vice President for Research and Creative Activity, Eric Muth, who joined the Ohio University in summer of 2024. And you can see his topic is planes, trains, and automobiles, the motion sickness side of travel. Please join me in welcoming Vice President Muth to the lecture.
Thank you. So I was both excited and nervous to be here today. Excited because I got to talk about science, and nervous that I really haven't talked about my science for a long time. But I was looking forward to not wearing a suit, and then I realized the student awards is right after this. So this morning, as I debated about wearing the green T-shirt, I at least wore my Einstein stock so that I would be smarter. So hopefully the title, I played with it, Planes, Trains, and Automobiles. For those of you that have been on the earth for a while, know that's a play on a movie. And I'm hoping that we're going to go on a little bit of a journey today where I teach you a little bit about the vestibular system and the visual system and the proprioceptive, and meanwhile explain why you get motion sick and answer any of your questions. I've worked in this area for a long time. I'm an international expert in this, and I don't say that lightly. And I'm affectionately known by a big company that I consult for that I can't talk about as the vomitologist. So I won't be talking about that today, but I'm happy to answer those questions. So before I get to my first slide, show of hands, how many of you get motion sick? Don't be ashamed. Okay, so how many of you have never been motion sick? Okay. And how many of those with your hands up have a non-functioning vestibular system?
A what?
Okay, so you don't, or you would know, and I can guarantee you, so more on that later, that I can make you motion sick if you wanted me to. And I'm going to tell you how, but we won't do that. So. Okay, so the talk is going to cover motion sickness, what is it, what causes it, and why, though? Why on earth should we get motion sick? That's a really important question that we'll touch on, and some possible ways for those of you that showed up wanting to know why do I get sick and what do I do about it. We'll talk about that a little bit, and I'll answer some questions. This is a little aviation slide up there. So I was in the Navy after graduate school, and spatial illusions and spatial disorientation and getting messed up in an aircraft goes right hand in hand with motion sickness. There's not enough time for us to talk about that, but that's why there's an aviator up there wondering what is up and what is down. And you will see an intersection in some of the things that I mentioned today about spatial disorientation and illusions, because they're related to why we get motion sick as well. Okay, so what is it? The next audience question. So everybody, close your eyes for a second and point on your body to where you get motion sick, for those of you that do. You have to do it. Everybody has to do it. This is a participatory talk, okay? So now everybody open your eyes and kind of look around at your neighbors. Some people are pointing to their stomach. Some people are pointing to their heads. So that's the challenge, is motion sickness is not the same thing for everyone. I've actually worked on a couple different motion sickness questionnaires. One was really a nausea profile. I got into the motion sickness business because of studying nausea, and I'll come back to that later in the talk as an example. And what we realized with both nausea, which is kind of a subset of motion sickness, and nausea to vomiting is not a continuum. Some people just go straight to vomiting. Some people suffer from nausea, which is awful for a long period of time, and never vomit. But it's a syndrome, and it's a syndrome with dimensions. There's this gastrointestinal, stomach, queasy, nauseated, like I might vomit component. There's a central component, faint-like, lightheaded, disoriented, dizzy. All those symptoms, you can experience multiple dimensions or a single dimension. What you experience can depend on the stimulus that's making you sick, so it can vary. Peripheral things like sweaty, cold sweat, hot, warm feelings, feeling like your vision's blurred. And one of my favorites, soap height syndrome, which we could do a whole talk on that, feeling annoyed, irritated, like you can't concentrate, drowsy, fatigued, falling asleep. We all do what with babies? When they're irritated and upset, Rock them to sleep. Motion causes stimulation to the visual vestibular interactions, and at certain frequencies, it's calming and puts people to sleep. At other frequencies of motion, it's very sickening. If I don't talk about that, someone remind me to talk about frequencies. I don't have a slide on that. So, and please, if you have questions as I go through any of these things, please ask them. So what causes motion sickness? The major theory of motion sickness is called sensory mismatch theory, and it says that basically there's inputs coming to the brain that disagree from our sensory systems, and the brain's trying to figure it out, and if they disagree too much, the body doesn't know what to do with it. It's a non-compute situation, and the answer is to get sick. What does that mean? So you have, I'm going to talk a lot about this, visual, vestibular, and proprioceptive systems. These are your sensory systems. We have redundant sensory systems, so they're providing similar information that has to get integrated in the central nervous system and in the brain. And do we have one eye? No. How many vestibular systems do we have? At least two. Depending on how you count them, there are more than two. So even within the visual system, there's redundancy. Within the vestibular system, there's redundancy. Where are the sensory organs in our body? They're all over the place. And even there's now information coming out that even like there are motion sensory organs in your blood flow. So the point is these proprioceptive sensors, there's all kinds of redundancy all throughout the body. We don't even really understand all of those sensory inputs. So they can easily start to mismatch. So if they agree, you're very happy, your brain's happy, and you're upright and you're able to navigate the world. If they disagree, we start to have a problem. So I like to use the AKA, the automobiles part of the story to illustrate what sensory mismatch is, because it's super easy. So a driver of a car, so your inner ear, and we'll get into the sensing that happens, and I can re-talk through this example, but the inner ear is sensing accelerations, turns, up and down motion of the car. It's sensing it. Your visual system, you're looking out the window, you can see where you're moving, and your proprioceptive system is attached to a steering wheel, so your muscles and your arms and hands are feeling the steering wheel and the movement of the steering wheel as you go down the road. Everything's aligned, visual, vestibular, proprioceptive, and even anticipation. I know, so even some of these other cognitive or mental things that are laid on trying to align these systems are all aligned. And does anybody get motion sick driving a car? So, you can. This actually surprised me. And one time someone came to me, they drove short track race cars. And they asked, why am I getting sick? And that's really complicated. It gets into G effects of racetracks and centrifugal forces. That's probably why they get sick. And accelerations and decelerations. So I'll talk about that frequency. So there was a lot of work done in the military about why people get sick on ships, which wasn't on their plane. That's why I'm not talking about it specifically. So on ship motion, everybody thinks it's the rocking and rolling that makes you sick. But it's actually up and down linear oscillations. And there's been all of this magical work done around 0.2 hertz, which is about 12 times a minute. It happens to correspond to respiration frequency, which is quite interesting. So this 0.2 hertz, if I oscillate you at 0.2 hertz, I think the stat is 50% of people oscillated at 0.2 hertz over something like 6 feet of throw will vomit. So they did a lot of work around that frequency, and it's quite magical. I can oscillate you in a linear fashion. And those of you that know a lot about the brain and the vestibular system, as we get to that, it's probably related to hindbrain activity. And there's something really bad in our development, an evolution over time about that frequency that wants us to avoid it. Okay, so you're 100% matched. Now, when do you start to get a mismatch? Well, when you move from the driver to the passenger, I now lose something. what did I lose?
Control.
I lost my proprioceptive and I lost that anticipatory response. So I can't always know what's going to happen. Am I going to hit the brake and there's those accelerations, decelerations? Am I turning a quarter? So I start to get a mismatch. How many of you, so I only had, I think, one person raise that they've got sick as a driver. How many people get sick as a passenger? So a few more hands go up. So there's this mismatch is starting to happen. Now the next one, I'm riding in the back seat. And no longer is it just I'm riding in the back seat. Now I'm riding in the back seat. I'm looking at my phone, which now involves head movements, which are opposite the car motion. But I'm usually looking at the back seat of a headrest. I'm not looking out the front of the window. If I am looking out of the window, I turn my head, and that's a different problem around vection that we're going to talk about with trains in a minute. So what now mismatch am I starting to have? Where is it? Visual. So now I'm losing that proprioceptive. I'm not grabbing the steering wheel, the anticipatory cognitive that's going away, and my visual system is doing something else. So I start to lose that, and you get this greater mismatch. That's what sensory mismatch theory is. And those of us in the field like to say it explains everything and nothing, because when you try to test it, it's super hard to test and validate. So it's a great theory, but it is a good explanation of the how you get sick, and it does correlate with degree of sickness. There are some other very good theories out there that I'm not going to jump into too much today. Okay. So now I'm going to go back. I want to go back one just briefly. The next few slides, I'm going to get into some specifics about the visual system, vestibular, and then proprioceptive, and talk about their individual involvement before I start to bring it back together with some examples. So the visual system. It's important to understand that from my perspective and folks like me, the purpose of the visual vestibular interactions are to stabilize the image on the back of your eye, the retina, so that you can see. Otherwise, you wouldn't be able to see anything. And when you think about that, it's really complicated to happen. And it happens in really amazing conditions. So your vestibular system is always telling you when you move your head around, telling your brain to what to do with the eyeballs. So when I move my head left, my eyeballs have to move right. And when I oscillate back and forward and side to side, in order to be able to see, my eyes are actually moving in my head. So my inner ear is telling my brain to move my eyes. The same thing happens when we're walking, believe it or not. So when we're walking, our vestibular system is telling, it's harder to observe it in someone, but they're telling our eyes to move up and down so that we can see straight ahead. It's also true, it's ocular torsion, so these are nystagmus movements. There's ocular torsion. When you rotate your head, your eyeballs turn a little bit. What's a challenge for your eyeballs as they move about your head as you move your head around? Time. That's an advanced answer. That's a give her 3 T-shirts for that one. That's a great answer. Lag time between the input, my head input. You have to have the vestibular system is a measurement input, goes to the brain, has to give an action to the eyes. There's latency in there. It's about 12 milliseconds. So I'm also not talking a lot about helmet-mounted displays, but I can and answer questions about them. And it used to always be that lag time in helmet-mounted displays was the big target. If we get it small enough, we'll stop making people sick. Well, even in your human system, there's latency. So, and it's measurable. It's thought to be around 12 milliseconds in the human. That wasn't the one I was going to say, though. What's another limit as I move my head? Yes?
Ability to focus it on small, you know when ballerinas spin?
Yes.
And focus, they're supposed to look on one spot.
Yes, so if I'm turning my head, and I'm not going to do that too many times, I'm going to fall, ballerinas, dancers, ice skaters snap their head around. So you're on to the limit, but what is it? I can only do so far with my eyes before I move my head. They can't go so far. They have limits in their orbit. So that causes particular challenges. That was a great example. Dancers, ballerinas. This is where my motion career started, in an optokinetic drum. And I tried to find an actual picture. I couldn't go back in my archives and find one of the drum I worked in as a grad student. But what this was a physical device hanging over the person. This cutout wasn't there, but it's there to show you the inside of the drum is lined with vertical black and white stripes. This drum, when it rotates around you, causes illusion called vection. This is circular vection. There's linear vection. So all of us have experienced linear vection. The car's sitting next to you, you're at a stoplight, you got your foot on the brake, the car next to you moves forward, you feel like you're rolling backwards. Everybody experienced something like that? This is circular vection. So in this, the drum's rotating around you, and you always feel like you're moving in the opposite direction. What happens is your eyes are tracking those stripes to the end of their ability to do so, the end of their orbit, and they snap back. So you get what's called optokinetic nystagmus. Your brain has to do something with that. Your brain is saying, why are my eyes doing this? And now you're creating this mismatch. My butt, I'm sitting in a chair, is telling me I'm not moving. So my proprioceptive systems, my muscles are saying you're sitting still. My vestibular system saying I'm sitting still. My eyes are saying I'm moving. And so this is the bizarrest thing. You start to feel like you're moving. Even in this situation, this particular drum, although it's not easy to create, you have levels of saturation. In immersive environments like helmet-mounted displays, we call that immersion. Here it's very similar. You get immersed in the illusion. So here you feel like you're moving 100%, but there's degrees of complete vection would be I feel 100% moving, non-complete, I feel like I'm moving but not 100%. This drum that we used in grad school was so powerful, you would look down and you still felt like you were moving. Because this optokinetic nystagmus is really driven by what's happening out in your periphery, not what's happening in what's called your frontal vision or your fovea. So your periphery, it doesn't matter whether you're looking down or not, you still have this big stimulus, and you feel like you're rotating. We use that drum to make people nauseated and study nausea. So we would take healthy undergraduate subjects, and we would bring them into the lab, we would make them nauseated, we had a lot of controls in place so that we didn't make them vomit, and then we had to sit in the, and we did have IRB approval, and we would study, I'll talk about the electrogastrogram later, and study nausea. So when I was doing that in the lab, I was not an expert in motion sickness, but when I joined in, I didn't know anything about the vestibular system. I'm going to tell you why later, and so then I went in the Navy and I hung out with vestibular scientists and visual scientists and learned a whole lot more. So,
Little question.
yes?
If you close your eyes, you would still be nauseated?
No, gone, broken. That's the way to stop it. So if you close, this is a 100% visual illusion, you close your eyes, and that's a preventative measure I'm going to talk about later. So you're closing your eyes, stopping the sensory mismatch, because immediately your proprioceptive system and your vestibular system will take over, and your brain will say, hey, I'm not moving, and it goes away immediately. And it's another important point. How many of you think, and I saw your question back there, so I'm coming back. How many of you think, can blind people get motion sick, or yes or no, based on what I've taught you so far?
No.
Yeah, absolutely can. The only people that cannot be made motion sickness are if you're labyrinthine defective, and that's 100% labyrinthine defective, and they have to rely on their visual systems to navigate, have a lot of trouble falling. So it's extremely rare, used to happen when we were doing these pretty invasive surgeries to the brain that we don't do anymore. Yes, well, we have one back here, and then we'll come up front. Yes, ma'am.
So do people, when they do VR, like video games, do they get as motion sick as that example, or do you know?
So that's a very good question. Field of view is important. So if you're doing a video game on your phone, with a small field of view, you won't really get this illusion. You won't feel vection. Now, you might get sick for other reasons. If I'm walking, doing a video game on my phone, if I'm sitting still doing a video game on my phone, probably not going to get this, although it's not impossible, but you're not going to feel vection. But as monitors have gotten bigger and bigger, and then as we put people inside helmet-mounted displays, then we brought in this term called effective field of view. So even though the display might have this much field of view when it's mounted on my head and it's driven by a sensor, it has its own sensor, that I have a fully 360 virtual surround that is sensed by my head movements and it's changing the monitor. Now I can have a 360 virtual surround and you can get more vection. It's still not as complete as that, but you can do it, and as the large, but you really have to get out here in the periphery. And most of when we've gone to the commercial HMDs that we have now, they're really a quite limited field of view, and they're not really out in your periphery. They're relying on head movements to get the full immersion in the game. But if you move your head fast, there is something that can happen. I love this one too. There's an article about this, and it absolutely works. And if you want to play around with it, feel free. You can make yourself sick there's an article and study on self-induced motion sickness. In a perturbed stance, you stand with your hands on your wrist, and just like dancers, so you have to lock your eyeballs in your head and pick a point over there and a point over there, and you oscillate back and forth with your eyes locked, which is the hard part. And if you do that at 0.2 hertz, you'll probably fall. So because you're using this vection illusion and standing still, and you can't...
Do you have IRB approval? Can we get our undergraduates to do this?
Don't do it now. We could get approval. We would have to give you a safety harness to be able to do this study. Yes, sir.
I believe you said that as we rotate our head back and forth, the vestibular system is responsible for moving the eyeballs. But
Telling the brain to move.
Okay. But I'm wondering, why isn't the bigger factor simply that I want to track the thing I'm looking at and keep what I'm looking at centered?
Well,
and so that would be just a visual thing, not the vestibular, wouldn't it?
right. So you have something normally. So this is one of those illusions where you're being tricked to do something you don't want to do. So I started to tell a great example about visual vestibular interactions, which is of quarterback throwing a football to a receiver, and I got to come back to that. But the example that comes to mind with what you're saying is like if I'm tracking a rabbit running by me. So I have some object out there moving in the world that I want to track. What I do is when it's in my visual field, that's great, but it's going to move out of my visual field. I'm going to move my head and track it like this. I'm going to follow it. So my head is going to follow it so my eyes can stay stable. This doesn't allow you to do that, so you are trying to track, but because it's a uniform black and white stripe, moving your head doesn't do anything, and you can't really move if you could sit there and spin at the same rate that the visual environment was tracking, then everything would stabilize, you'd be fine. Did I answer your question?
I'm not sure. You're
Okay.
this thing. I'm just thinking.
Yeah.
Rotating
Yeah.
the head or looking. I'm just trying to keep the screen centered.
Yeah. Well, that's a different thing. You're just trying to focus on it. So, right. So, in the trains example, so there are other reasons like accelerations and decelerations that cause you to get sick in trains. But one of the very powerful things in trains that you have to be aware of is vection. So in trains, immediately that control and the proprioception part is taken away. This happens in planes as well, but in trains, I mean, you're on a vacation or you're traveling by train, it's slow. Unless if you're training by commuter train in the city, you're going to work, you're doing your reading, whatever, you're not paying attention. But if you're on a train and you're going across country, what do you want to do? look out the window. I want to see what's going by. And now you create this problem for yourself where you turn and look out the window and the world is going by you the same way that those stripes go by you. So trees are going by you, fence posts are going by you, and you start to have vection. The same thing happens if you were standing on a platform or standing still in a train and it moves by you, and it can be very powerful, and you can actually get nauseated very quickly. You just close your eyes and it goes away. But if you don't know to close your eyes, then you won't do it. And so here's another visual trick about closing your eyes. Nothing to do with motion sickness, but it's a very good trick to know about night vision. So when you get up in the night and you have to turn a light on, close one eye, and you'll maintain your night adaptation. So when you flip the light off, your eye that was closed will be 100% adapted, and your other eye will be washed out, and you won't be able to see. So little tricks like that, they seem obvious, but until somebody says it to you, you don't know to do it. That's my favorite one, because I do that all the time so that I can operate in the night. For what reasons, I don't know.
There's an interesting question there.
So let me move on to vestibular system, and this is going to start to get some of these other questions. I got to give you a little bit of education. I'll start with my story. So I had taken some biology classes. I switched to psychology, thought I was going to be a biology major. I did take physiology, so I learned about these things. By the time I got to grad school, I should have known better. But every time you open up a book and they talk about the vestibular system, it looks like this. Nobody ever shows you where is it in your head. None of the books ever say the obvious thing that this is a 100% redundant system and there are two of them, one on each side of your heads. So until I get in grad school and somebody starts talking about this that knows what they're talking about, goes, oh yeah, we have them on both sides of our heads. I'm like, oh, I never thought about that. So you have to be careful with these complex things. There are simple things that can really get in trouble. And I think my laser, well, there it's back. The vestibular system is immensely complex in and of itself. So this is just one half of the vestibular system. I want to say that. One side of inside the inner ear. And then you have your canals and your otoliths in here. Your otoliths are sensing linear movements and your canals rotations. And I'm going to talk about that in a minute. But we always have to remember there's one on each side of our head. So when we look at ourselves in the mirror and we might get frustrated because are our eyes exactly in the same place? If I drove a post down through your body, is your right side exactly the same as the left side? No. And just like that, your vestibular system on the right side is not exactly in the same place. I'm talking exactly if I drove a rod down through the center of your mass in your body as your other side is. So that can cause big challenges because we can have big vestibular asymmetries that we don't know about. Now, when we started learning to crawl, walk, and run, and little kids do all kind of crazy things, like spin around bats and run and try to go straight that you make adults do, and like, why I'm not doing that? Because kids' brain hasn't fully myelinated. Their visual vestibular connections and visual vestibular actions aren't all developed, and you haven't developed all these schema in your brain and pathways to know that those things are not really bad to do. So kids will do them. So your brain, as it develops and fully myelinates, masks a vestibular asymmetry if you have one. Has anybody had an experience in their life where they didn't get sick, and then they went and did something like rode a ride at an amusement park or rode a plane for the first time and you got like terribly sick, like vomited? So it's possible that what happened in that instance is for the very first time, your brain was revealed your vestibular asymmetry. And now our brain, thankfully, is adaptive, and as long as we don't stay in that environment, then we're going to readapt. We're constantly readapting to the environment we're in. But in some people with extreme vestibular asymmetry, it's thought that could cause lingering after effects if you're exposed to something extreme like hypergravity. So let me talk about what is each part. I'm not doing a physiology lesson. We're talking about functionality. So what do each parts of the vestibular system do? So the canals are your roll sensors. So yaw, pitch, and if I could roll myself, roll, pitch, and yaw. So the canals are like big tubes filled with water. So if I put a big pipe on my shoulder with water in it, if I tilted it, the water would tilt back and forth. If I started running, the water would also tilt as I accelerate until I reached a stable acceleration, which is hard for humans to do. Vehicles do it, but humans don't always do it. And then I stopped, it would move again. So that's how the canals operate. They're filled with fluid. The fluid moves around these circular tubes, and there are sensors in there that sense the movement of that fluid. And when it's moving, we get rotation. Interestingly, in space, I'll come back to the canals work just fine. So that mechanism of water in a tube works when there's no gravity. I know there's at least one space fan in the off. So the otoliths work very different. This is terrible. It's too dark for here, but you can see the critical part. So you have hair cells sitting in like a gelatin block. And there are little crystal-like things in there. So now when you tilt your head, what happens is those crystals in the gel don't really move, but they bend the hair cells. So they bend when you tilt forward and back, and accelerations also bend. So the otoliths are detecting forward, back, right, left, and tilt movements. Interestingly, so what happens when we ingest some toxins, maybe say like if this were a different venue and we weren't having coffee? Does anybody know what happens to the vestibular system? With alcohol, yeah.
Can we guess that it shrinks?
So what happens is, it's a good guess, what happens is it messes with that gelatinous layer. So it actually messes up the fluid composition in that layer. So now the hair cells start to bend in unexpected ways that resulted us not being able to walk straight lines and often trip and stumble because you're having alcohol has a direct impact on the otoliths. Toxins, that's going to come up later. In terms of the vestibular apparatus, if you look at evolution, if you look at older organisms, this is the older organ. The otolith is extremely, extremely important for us to maintain upright and be able to walk and move throughout our environment, and it's critically important to other organisms. And the wiring in the brain is likely older for this. So when you start messing around with this organ, it can hit you very quickly. All right, so I'm coming back to that example now. Just going to check time. Okay. I'm coming back to an example of how does this otolith canal thing interact, and how could we have a conflict just within the vestibular system? So now his eyes, he's kind of maybe has them closed. They're supposed to be closed. This was just a picture when I was doing work in the Navy. This is what's called an off-vertical rotator. So it's a chair, but I can put you in the chair and I can tilt you. And then I can rotate you at very precise speeds. This actually has a track, and I can take you off center if I want to be super cruel. But in this case, you're on center of axis, just tilted. So if I'm rotating, what are the canals going to tell me? They going to give any information to the brain? This is a test part of the conversation. So I'm rotating, what are my canals? So I'm spinning like this to the left. What are my canals telling me? If no acceleration, they wouldn't give input. Great point. They're going to give me only input when I'm accelerating. Once I'm at constant speed, they're telling me really nothing. If I'm right, so if I'm on level, not tilted, and I'm rotating, once I get to speed and I'm holding you at 10 RPMs, you will say you're not moving. If I stop you, suddenly you'll say you're moving in the opposite direction because they slosh back. So now if I'm rotating like this, What are my otoliths telling me? Are they giving any information? Not like this one. I'm just saying if I'm straight up and down. I'm going to get to the tilt in a second. So I'm rotating, just sitting in a chair. Are my otoliths giving any information? No, no information. So there's just zero, nothing's happening. So I'm rotating until I get to constant speed, and now I'm not rotating. Okay, now I take you and I tilt you off vertical. And you have to use your imagination. I don't have a video, I have a little picture. So you can see in this picture, I'm facing up. In this picture, I'm facing down. I'm rotating at a constant speed. My canals should be telling me I'm not moving. But I do have this going on because I'm going from here to here. So I'm doing this. So my pitch is changing. So one of my canals is getting an input because it's roll, pitch, and yaw. We were only talking about I'm not moving in yaw, but now I'm moving in pitch. So I am getting a constant change in pitch because my head's moving. And my otoliths are telling me your head keeps tilting forward and back. And your brain goes, what is going on? I don't know what's happening to me. How many of you have ridden the teacups? How many of you ridden the teacups as a kid and loved it? And how many ride the teacups as an adult and say, never am I going to take my grandkids on it? You still love it. So this is like riding the teacups. So the teacups are actually, this is the engineers in the room. Engineers love to think about how we can move people and put devices together and move them all different ways. And the teacups, and some of them are flat. Most of the ones you see today are flat. You just kind of rotate and spin. But there are versions that actually go tilted, and so you're spinning and tilting, and that's what this is. So the most sickening motion, and this is also probably tied to evolution, is called barbecue spit rotation. So if I take you and lay you horizontal and rotate you, almost everybody will get sick. You know, I think probably we didn't like getting put on spits over a barbecue pit. And maybe there was some adaptation to those that survived that said this was probably a bad place to find us.
Are roller coasters the same thing? Because they do some crazy things very fast.
Can be, but the speeds are usually such that it's more accelerations and decelerations and gravity vector. And I'm going to come back to that in just a second. So this motion, just to resolve it for everyone, the movement feels like you're walking in an ellipse while spinning. That's what your brain actually, and try to do that for 5 minutes. And so that's what it actually feels like to your brain. And your brain is just going, does not compute. It's a huge mismatch. And the further the tilt, the worse this is. So that's an example. We talked about this sensory mismatch. That's taking it to the more complicated level where you really have these interactions. Okay, so now we've covered visual system, we've covered vestibular system, now seat of the pants, proprioceptive system. This is the easiest one. I know this is where we're all getting tired and hungry, so I left the easy one for last. So this is seat of the pants feel, we call it in the aviation world, because that's where it messes you up, where you have a change in gravitational vectors. Usually, seat of the pants treats us very well. We're sitting in a chair, we have our arms on the table, and the question about virtual environments earlier, there's great research that shows that when you're measuring balance and stability, and you want to get more stable, I just have to do that. Just have to have one more point. And it doesn't have to be a hand. So our proprioceptive system is so good, just adding this small bit of redundancy will help stabilize my posture. So this is really good in 1G, normal gravitational vector environments. So when we couldn't fly, it was no problem. And when probably, when we tried to fly before we had planes, that was probably a bad situation. And those people that thought that they could fly got removed from the gene pool, and we didn't have to evolve to adapt to it. But now we get in planes. Now we get on roller coasters. Now we get on centrifuges. All these things which work by holding us into place through centrifugal and changes in the gravitational vector. Even on a plane, when you're in a normal bank turn, there's a gravitational vector that is telling you down is in your seat. Always when you're on a plane, if you have the windows closed and I ask you where down is, if you tell me it's not in the seat of your pants, the plane's having a problem, because that's what keeps it in the air. And if you don't feel that down on your bottom, then the plane's got a problem and you're falling out of the sky. So it's very good at telling us where down is. It's a very strong sensation, and if you have a disagreement right away. So if I have a disagreement, my brain's trying to resolve between my visual system, vestibular system, and proprioceptive system, which one does it believe? Which do you think it's going to believe the most out of those three systems? Visual system. So it's really, really hard for our brain to ignore what we're seeing. But for pilots that can't see, so if I take the visual system away, this seat of the pants feel gets pilots in a lot of trouble. So the biggest time accidents happen in aircrafts, not for big aircrafts, they're well trained on using radar navigation systems and they got fancy equipment up there, but for single jet engine planes, single engine, twin engine planes that are pilots flying that are not instrument rated, when you fly from visual flight rules to instrument flight rules, from visual meteorological conditions to instrument meteorological conditions, there's a transition. You have to switch to instruments, and there's a problem with the way the instruments are designed from a human factors problem. It causes control reversal errors, which is a whole nother talk. You start to go, okay, where is down? And you start to rely on this, and you start to put yourself into a controlled bank turn until you get into a death spiral and fly into the ground. And there have been famous cases of that happening. Okay, so I'm getting to time, so now I've talked about gravity. I want to talk a little bit about how gravity makes you sick. So this is an experiment we did. NASA KC-135, the planes, it's called the vomit comet. Everybody knows it for training astronauts going up and down in parabolic flight. And at the peaks and troughs, you have less than 1 G, so you can become weightless and you can float around. Well, my creative team in the Navy, and I didn't design this, I hopped onto this project, we did this, not quite. We flew in a normal bank turn at 1.8 Gs, so the turn was, this was a 2 nautical mile turn, really slow, normal banked, controlled turn, but constant G. And one team was looking at ocular torsion, that what I was describing. My team was just asking a simple question: does this make you sick? And again, like that oscillation, when we moved people, when we oscillated people in a similar chair, but we had to move it by hand, we had a huge number of people unexpectedly vomit. We didn't think it would be so sickening. And so then we started to learn. We always knew in space that when you unload the otoliths, so they don't work, your brain has to rely just on the canals in your visual system in space. So you'll hear astronauts talk about, and if any of you fans of Ender's Game, you know that movie Ender's Game, and they say the enemy's gate is down, that's the same thing. You have to define what's up and down for you. So if you cognitively, you define it in your mind, in your brain, and then your visual system knows, and everybody knows that's down, and you can just let go of our normal cues of a chair tells me that's down, because they're all strapped down, everything in a shuttle. So if I define it, I really get okay pretty quickly, and I can adapt to it. But if I don't, my otoliths are useless, and I'm relying on my canal visual interactions, which are kind of disturbed, and we don't do a lot of large spinning movements. So things like my rotation and the optokinetic nystagmus, my eyes still work. I can still see the thing I'm trying to look at. But my up and down sense and sense of tilt is all messed up in space, and it's terribly sickening. And even when we did this experiment, and I was just fooling around, they were paying for this experiment. I think it cost like $1,000 a minute to fly that plane, and that was a long time ago. I just tagged on, and we found something unexpected. It was pretty cool. All right, this is, to me, the most important thing for those of you in the room that get motion sickness. But, all right, Eric, you told me all this stuff. You talked about the vestibular system and the inputs, and you threw out this theory. But why do we get vomit to motion or feel nauseated or feel terrible? And a thing about nausea, a little sidebar, is nausea from a psychologist's perspective. We talk about conditioning a lot. Nausea is the thing that conditions you to get the heck out of the environment you're in because it feels bad. Vomiting makes you feel better. So it's not the vomiting. We all don't want to vomit, and it feels terrible if you're, we want to vomit, but we can't. But it's the nausea that's the conditioning. But why should that happen in motion? It makes sense if we're sick or we've had a poison. Well, the main theory on this, and there's a lot of traction on this one, is called Treisman's theory. That motion sickness is an appropriate response to an inappropriate stimulus. So motion has triggered with these visual vestibular interactions things that happen when you're poisoned, like the direct effect of alcohol on the otolith. So your brain is going, what is going on? I'm getting these senses, and Treisman's toxin defense, you have many levels of that. This hits the 4th level, if I'm remembering correctly, so you see things that look putrid. I'm not going to eat this animal that has maggots all over it, that's bad. Then you see something, well, it doesn't look too bad, but you smell it. So you have sensory, that's a 1st level defense. Then you put things in your mouth, you taste it. Oh, tastes bad, spit it out, 2nd level. Then you get it into your stomach, and your stomach actually has receptors and go, whoa, I don't know what you just put in here, but it must be loaded with bacteria. I'm going to get it out of here. But then stuff that makes it past all those levels starts to get into your bloodstream and starts to have direct toxic effects on your body, and that's the 4th level defense that Treisman believed is triggered, and that's why motion makes you sick. It's just an accident. It's just an evolutionary accident. What's interesting in some evidence, so you think you've been poisoned and you want to get sick to get it out, or more importantly, there's another great theory that talks about you don't want your brain to adapt to emotion that you don't normally experience. So there could be a good reason for this that's not just accidental. It could be to get you out of this environment that we don't want you to adapt to permanently. So that's called mal-de-embarkment syndrome on space or a ship. So if you've ever gone on a cruise and not gotten off the ship for 10 days, you get off the ship, you don't feel good. So you adapt to the ship, then you don't feel good. If you go to outer space, if you notice they don't ever really show the astronauts, or they show smiling faces and little waves and then they cart them off, that's because they have all of them have mal-de-embarkment syndrome, and they don't feel good, they can't walk right because they have to readapt. They've been in space, they've adapted, and you will adapt if I put you in that environment and you can't get out. So you will make it through that period of I don't feel good. And so it could be that you're feeling these things to get you out of that motion environment. If you can't get out, what did I say happens to babies? You go to sleep, you fall asleep. So now I'm not developing new neural sensory connections and patterns. So sleep is also an adaptation. In terms of toxic defense theory, there are a couple things that support this. Asians are hypersusceptible to medicine, alcohol, and motion. Margie Prophet has an interesting theory about pregnancy, that you get sick in your first trimester of pregnancy to sensitize you and reduce your diet, because that's the area where the infant, in its development, the fetus, is most sensitive to those toxic effects, which also plays into the same space. So there's some, I feel this is probably accurate, although this other really good vestibular group put out, nobody ever has really researched or picked up on it, this alternative idea that no, it's just to keep you from going in that motion. And as we get older, remember I used a teacup example or circling around a bat, we as adults say, I don't want to do those things anymore because our brains are fully myelinated. We don't want to be challenged in those ways. We do, in fact, avoid those environments. Okay, so how to prevent it? We've already talked about a couple things. Minimize the sensory mismatch. So if vection's bothering you, close your eyes. If you're bothered riding in the back of a car, don't read a book, don't work on your phone, don't look out the side window. Close your eyes, take a nap. So whatever you can minimize the mismatch, try to minimize the mismatch. It's not always easy, okay? So the one other thing, and I'm going to go quick here, so I'm happy to talk about it. So one of the things I worked on, I'm actually a gastrointestinal psychophysiologist by training. This is a fluoroscopy picture of the stomach, starting with picture 1, 2, 3, 4, 5, 6 around here. This is a measure that's called the electrogastrogram, which is like the EKG of the stomach. You measure it from the surface. What you're seeing in the stomach, it's oriented this way, is contractions coming down the stomach. And the stomach contractions both circularly and longitudinally at the same time. And here in the side of this is an electrode, this circle. That's an electrode on the surface of the skin. And what you see is that there's we can measure this from the surface. And this is a 3 cycle per minute rhythm that we see when we have a happy stomach. So when we're fed or when we're between feeding, we go in and out this. There's called the interdigestive complex. But we have this happening. It's what paces contractions when they occur. It's not contractions, but it paces them. When we get sick and nauseated, this turns to 4 to 9 cycles per minute. So another thing you can do is try to keep a happy stomach, and there's been research done. Protein seems to be a good thing, like protein bars. I like to say eat comfort foods when you're traveling and just become a snacker. So eat the things that make your stomach happy, because we have a lot of individual difference. But there's some evidence that like protein has more a protective effect than carbohydrates and some other things. So to summarize things to remember from the talk, motion sickness is a syndrome. It's driven by sensory mismatch. It activates the body's toxic defense system. This is my favorite. There's no cure-all. There are some good drugs I'm happy to talk about, but no one has ever died from it. You feel like you want to, but you don't. And keep a happy stomach. Thank you. I have a question over here. Wanted to make sure I got through. Yes?
I was going to ask you about this 12-second resonant frequency we have, and I was going to ask you about this 12-second frequency or 12 hertz
per minute. So
12 hertz frequency.
Yeah, 5 seconds.
Yes, and the fact that we use all sorts of medicines like Dramamine and diphenhydramine and things like that for our vestibular, and you drink alcohol in it. So are there drugs that can affect this 12 hertz frequency? But then when you talked about the stomach contraction rate, it sounds like that's a factor of that perhaps, and maybe that's what's triggering it. Or can I just take Dramamine and not throw up on a dive boat?
Yeah, so this is yes and. So if you don't want to, so my advice is if you don't want to take medicine, then keeping a happy stomach, minimizing the mismatch, like on a ship, minimizing the mismatch is get on deck and look out over the horizon. Everybody wants to go under deck, but what you should do is look out on deck, get up there with the captain. If he'll let you drive the boat, be in control and look out over the horizon. But most of the medicines, and antihistamines is a big class, but most of the medicines have either an effect on the vestibular system or a direct effect on the brain in some ways that we don't always understand. They're more or less dulling you to the sensory mismatch. They're disrupting that so that you're ignoring some of the inputs. And my master's thesis was actually on Dramamine, and I've done other work on other devices, like there's AccuBands and electrical stimulation for the Niguin point on your wrist is the acupuncture point for motion sickness and nausea. If any of those things work for you, you should do them. You should do whatever works for you. Some of the drugs, like Dramamine, is very effective. It makes you sleepy. They all have side effects. Meclizine is a little less drowsy, but it's not as effective. Anytime you go in a drugstore, you can get these drugs over the counter now. It'll say non-drowsy version. Usually it's just a half dose, which means it's not going to be effective, but you'll be awake and sick. So I always recommend take Dramamine and just have a little bit of caffeine to keep, so you're trying to enjoy vacation. And the thing is, you usually have to do it ahead of time. So if you know you're somebody that gets motion sick, it's best just to start taking the medicine and have it in your system if you're going on a cruise. Drink a little more caffeine than normal to help deal with the drowsiness. And as your days into the cruise, if you're feeling good and everything's going okay, then stop taking the medicines or decrease it. There was a guy, I'm going to blank on his name, it's going to pop in my head right as soon as I stop talking. His idea, and he's not wrong, you saw in the motion sickness syndrome part of it, a big part of it is anxiety. So if you've got sick before and you're going on, you just spent $3,000 to go on a cruise and you don't want to get sick and ruin your vacation, you're going to be immensely anxious, was going to affect your brain and your stomach, and you're not going to eat right. And so his belief was that if you remove the anxiety part, you could almost cure motion sickness. So there is an anticipatory effect. So that's why you want to take those drugs on board early, because once you're getting sick, you would need even more powerful drugs to stop it from happening. Great question.
So my question is for those of us that don't get motion sickness.
Yes.
What's wrong with us? I mean, are there genetic predisposition? Are there certain genes implicated in motion sickness? Or, again, what's wrong with us?
Yeah, and I'm glad you said it that way, because for all of those you do get motion sick, you shouldn't feel bad, because it's very adaptive. It helps protect you from injecting toxins and other things. So for those folks that kind of don't get motion sick, again, I would argue it's not that you don't get motion sick, you just haven't been exposed to the right stimulus. So you're motion tolerant, and you have a high tolerance level. And why is that? It could be lots of things. I'm not aware of genetic markers at this point, but are there some? Probably. But more than likely, you may have better asymmetry, and you may have challenged your brain in a way when you were a kid that you adapted, although you can become sensitized, like because of all that rotation stuff I did. I'm kind of sensitive to rotations, but that's probably the anxiety part. So it's not really known, at least I'm not keeping up with the literature now. That's a problem of wearing a suit. You lose track of some things. But it's not really known why. But my answer is, if you want to get motion sick, we'll make you.
All right. Let's thank Dr. Muth again for fascinating subject. Thank you very much.
Thank you all.
And if you want a T-shirt and you were too shy to ask a question, Rox is going to be happy to give you a T-shirt. So thank you, Dr. Muth.